Thank you.
Thank you, Charles.
So much. All right. Wow. Well, I'm really excited to be here. Let's see, I've got some slides to use, but I'm really excited to be here and tell you a lot about what we're doing at SpaceX and Tesla. And in particular, what I'd like to talk to you a little bit about is how we move so fast. That's one of the questions I always get, is how we move so fast at SpaceX and Tesla and do the development that we're doing. So the other question I usually get is how can you actually work at two companies like SpaceX and Tesla and make that work? Well, one of the reasons is because we have a very, very straightforward mission statement for both companies. So I always know what I should be doing to make that happen. And at SpaceX, our main mission is to become a multi-planet species. SpaceX is really a space transportation company. So one of the things that we focus on is how do we get the most amount of payload into space for the least amount of money. And if we're going to ever become a multi-planet species, we have to make tremendous gains on that. And so we take on projects that change those factors by an order of magnitude rather than looking at small increments like a few percent here and there. So right now, our Falcon rocket system is the main system we use to go to orbit. But our biggest work right now is on Starship, which takes the reusability that we use in Falcon and takes it to the full vehicle. So Falcon, we can only reuse the first stage, some of the fairings, but on Starship, we're going to reuse everything and be able to take over 100 tons to orbit or to Mars in a single flight. At SpaceX, or at Tesla, the mission statement we have there is to accelerate the world's transition to sustainable energy. So that has a number of components to it. We really have to generate renewable energy. We have to be able to store that renewable energy, and we have to be able to use that renewable energy in transportation. So it's very important that we hit all of these. Most people think of Tesla as only a car company, but we actually take it very seriously that we have to attack all of these aspects. And the other point of it is we don't need to be a successful car company. What we need to be is a company that accelerates the sustainable transition to renewable energies. And to do that, we can actually incentivize others to do it as well. And so one of our missions is to get everybody else to do the same thing. One reason why we actually open source all of our patents at Tesla to allow others to use the technology to get there. It's a big, big problem. You know, there's 90 million cars that are made a year. One single company isn't going to be able to do that. So we're very invested in making sure that we come up with those solutions. So every time I'm working on something, and I get to do a lot of really great, fun things, all I have to really do is make sure that what I'm doing is getting to these objectives. One of the ways that we do that fast is we kind of throw away the rule book. Okay, if you look at this illustration of how development actually happens in the aerospace world today, it's a very long process. And there's two features about this that I'll point out. One is it's a stepwise program. You have to do a concept first and then go all the way through to designing components before you actually make something. And then you start to make something and test something, and then you validate it again through components back up to the system. But by the time you actually test the system, you've put so much effort into it that it's very difficult to say, we've got to go change course. And in the concept phase is when you have the most flexibility to make big change and have big impact on what you're designing or what you're developing. So if you have to wait till the very end to do that, it's super costly and it takes a long time. So what we do at SpaceX is we really compress those things. We design and we build and test at the same time. And sometimes that looks messy, but what that does is that gives us feedback on our concept very early in the process, and we can make changes very quickly. Then we actually validate it in the real world so that we know how it's going to work in the real world. That's generally kind of costly because you have to build full systems and get them out there and start operating them before you are ready to sell those services to the rest of the world. But it's really the way to go fast. I'll give some examples of that. So in terms of going fast, this is our Starship program. And in April of last year was our first integrated flight test. Within just a few years of starting this vehicle program, we were able to get a system ready to go in flight. And if many of you were watching, that first flight didn't go so well. So, we put this system together, built the first stage, built the second stage, fueled it up, sent it off. First thing that happened was we basically destroyed the pad on that launch. We also had a number of the engines that didn't light and didn't work and failed. And we also had the second stage didn't actually get to light. So we went back to work and we decided to change things. We did a different staging system, what we call hot staging. We changed the way we operated the engines. We rebuilt the pad, and we made many design changes as we were already building the second one ready to go. So this was done in the course of 7 months, and in November of this year, we got back to the pad, and we're ready to launch. And so this was the second launch that we did just this last November, and this one went tremendously better than the first one. But it didn't go perfectly, and we learned a lot more from that one. So that one we actually launched. We had all 33 engines on the first stage operate flawlessly. We had all 6 stage engines on the second stage operate flawlessly. We staged properly, and the pad survived and actually performed very well. But now we're ready to go again. So 7 months from that first one to the second one, we're actually just about ready to fly. We should be flying sometime in February, 3 months after this one. So that's an example of how we build and test very rapidly at the vehicle level so that we can do that. We also have like 3 or 4 of these vehicles in production at one time. So right now we're able to take those vehicles and make the changes and be able to get back to the pad and test those again. So this is the second launch that we did in November. One of the things, the question is, how do we solve these problems so fast? How do we do that? One thing we apply is what we call the algorithm. It's really a 5-step program. And the first step is that we question all the requirements. So when we attack a problem, we ask ourselves, what are the requirements on this problem? Why are they there? We have a rule at SpaceX and at Tesla that a requirement can't be a document or from a department. It has to be from a person. And you have to be able to go talk to that person and be able to ask them, what are the physics behind this requirement? Why is it there? And if they can't answer that question, it's not a requirement. You don't have to design your part according to that requirement if they can't explain it to you. So that's the first step. The second step is to delete your part. If you're a designer, you have to design some system or part. The first thing that you can do is you can actually decide that it's not needed, okay? And that's actually the best outcome. So most people would say, well, aren't I designing myself out of a job? Actually, you're doing your job the best way you can. Because first of all, the best part is actually no part. No part has no mass, has no cost, and its reliability is perfect. So can't get better than that. So we have no part. As a materials engineer, I kind of expand that to say that the best process is no process. So if I don't have to do something to the part to make it, that's the way I want to make it happen. The third one is really to simplify. At that point, we can basically take all of the extraneous things out of that part and make it as simple as possible so that we can manufacture it quickly and we have less things to go wrong. If that doesn't solve the problem, we try to accelerate it. If we have a yield problem or something like that, we try to make it faster so that we can actually make enough or make it happen. And then the last step is to automate. So if we can't get it up to speed, then maybe we can automate the process and make it more reliable. So automation is actually the last step. If you think about kind of how problems are solved in general today, a lot of times in manufacturing, the first thing they do is go to automation. I'm having a problem with this manufacturing process. It's not fast enough. I can't get enough yield. I try to automate. Then if that doesn't work, you accelerate it. If that doesn't work, you simplify. So you kind of do this in reverse. I've seen it time and time again. And actually, in the end, sometimes you end up deleting a part that you've done all this other work on that shouldn't have even been there in the first place. So this is the kind of algorithm we use to solve problems very quickly. An example of one of those I'll give is the gigacastings. So when we were designing the Model Y, Elon came to me, had one of our toy cars that we sell in the shop, and he gave me this car, and he said, this is the way I want to build the Model Y. And I looked at this and I go, wow, this is a pretty big challenge. So he wanted to make it out of two pieces, essentially, and big castings. And so I had to go off, and at first I really didn't think this was possible, but I knew that if I explained that to him without the physics behind it, I'd have to go look for another job. So I went ahead and started to dig into this, and it turned out it actually wasn't a bad idea. This is an example of the underbody. We couldn't make it in one part. We actually had to make it in two, okay, based on some of the real requirements we had. But on the left, you see the stamped body. This is an example of Model 3. The Model Y was a derivative of that. That had over 100 parts in that underbody. And with a gigacasting, we could actually cast most of those features into the casting, and we could eliminate almost 80 or 90 parts and over 400 robots from the body line to manufacture that part. And we could do that. So this is the example of doing this all the way through to do a front body and a rear body. And we had about a 10% mass reduction, gave us a better 14% range opportunity based on that. And we had 370 less parts in the body. Essentially, now we can make the body out of three major components: the rear, the front, and the battery pack. So one of the other things is we have to move fast, so we have to come up with unique solutions. So we had a great design, but we didn't have a company that could make casting cells big enough, and we didn't have a place to put it in the factory. So we worked with a company in Italy to actually design this machine and get it there quickly. I actually had to rent a few Antonovs to fly over the tooling in airplanes to actually make the time, but we didn't have a place to put it. So I actually built the first outdoor foundry shop in an automotive factory when we had space in the parking lot. So this was the first castings that were made for the gigacasting project in Fremont, California, and we put this together in less than 8 months to launch this product. And this was the largest casting machine in existence at that time, but now the Cybertruck casting machines are another 3,000 tons bigger than these 6,000-ton casting machines. And that is basically 1/3 of the car body coming out of the casting cell every 60 seconds. All right, I'll talk a little bit about Starship. Trying to get through here pretty quickly so we can get to the round table. This is some examples of how we do simplification. On the left, you'll see the Raptor engine, first Raptor engine we designed for the Starship program. And then within less than a year and a half, we had built 100 of these engines and then redesigned it to the system on the right. And you can see that the system on the right has a lot less plumbing, has a lot less electronics on it, much simpler to build, and more reliable because of that. We're actually already in the 5th generation design of this engine, and almost all of that extraneous fiddly bits are going to be gone. All those features will be incorporated inside the engine. And the big win there is that actually lets us remove the heat shielding that we put around these engines in the rocket, and that allows us to build the rockets a lot faster. And in terms of being able to go to the concept phase and change direction very quickly, originally the Starship was designed to be a composite rocket. We thought that was going to be the lightest weight, most performance rocket that we could make. So we actually went through the process very early in the design of that system and built a composite cryotank. So this was a 12-meter diameter tank that we built. Took us about 6 months to build this tank, and we went out and tested it, and proof tested it and blew it up. We had to take a barge out into the ocean to do that because it had so much energy that we couldn't do it on land. But while it worked, it was great. It was lightweight. What that 6 months taught us is we never wanted to build a rocket that way again. So we went and actually pivoted at that point to a stainless steel design, basically going back to technology from the Atlas rocket days. But the benefit is we can now build one rocket, the whole booster, in 1 month. And that allows us to do that iteration very, very quickly. In materials, one of the ways that we can actually do this is through computational design. So we can actually model most of the materials that we're using today, and many of the tools have been developed over the last 50 years. We call that the materials genome. We can then put that into a design sequence that we call computational materials design. And what that allows us to do is we can then design the material, we design the component, and we design the manufacturing process all at the same time. So in the gigacasting project, before we even designed the car, we were designing the alloy that we had to make that casting out of, because it didn't exist. There wasn't a casting alloy that would work for that product, and we had to sign up for what we were going to deliver to the body team ahead of time, and then design that as we went along, and we finished up that design only a few months before we went into production. So this is kind of how we do things at SpaceX and Tesla and how we move so quickly. I like this image because this is an image that brings together both of my jobs into one project. It was a lot of fun. When we designed the Falcon Heavy rocket and launched it for the first time, you don't usually put a customer's payload on the rocket to test it with, in case something bad happens. But my boss donated his Tesla Roadster. This was serial number 1 for Tesla Roadster, and allowed us to launch it into space. So I had not only the benefit of working on the Falcon Heavy program, I had to figure out how to space harden a Tesla to get it out in space. This is now orbiting in between Mars and Earth's robot, and so it was definitely bringing all that together. It brought together a lot of very dedicated people to do that. And when people ask me what it feels like to do this job, this project is one of the ones, and our media team put together a really great video for this that hopefully makes you feel some of that excitement that we have when we do these kinds of projects.
It's a god-awful small affair to the girl with the mousy hair, but her mommy is yelling no, and her daddy has told her to go, but her friend is nowhere to be seen. Now she walks through her sunken dream to the seat with the clearest view, and she's hooked to the silver screen. But the film is a sad thing for she's lived it 10 times or more. She could spit in the eyes of fools if they ask her to focus on sailors fighting in the dance hall. Oh man, look at those cavemen go. It's the freakiest show. Take a look at the low man beating up the wrong guy. Oh man, wonder if you'll ever know who's in the best-selling show.
Not everything goes right.
Is their life on Mars?
All right. I really thank you for your attention today. Appreciate the chance to get to talk to you.